Okay, so I'm going to go over another way to do this problem we left off with last time when we were doing the radicals and rational exponents. Here it's not simplified because we have this radical in the denominator and we multiply by 8 to the 4/5. But another way to do this to maybe simplify it a little quicker is to rewrite this 8, the 5th root of 8, instead of 8 to the 1/5. 8 is 2 cubed, right? So here we have up top, we have the 5th root of 7. And then down here we have, this is 2 to the 3/5, right? And now how do we get rid of the 2 to the 3/5? Well, we got to multiply by something so that we get 2 to the 1st, really. Right? You can think of it that way. And in this case, we say, well, that means as well, it's going to have to be 2 to the 2/5. Right, so 2 to the 3/5 times 2 to the 2/5 would be 2 to the 5/5 or 2 to the 1st. So that becomes what I need to multiply by. Okay. And then when you do that, we have, and this is where, the knowledge comes in that here I see this is a 5th root, right? Because I have a 5 in the denominator here, that's a 5th root. And if I have a 5th root times a 5th root, I can put them under 1/5 root. So I have the 5th root of what? 7 times 2 squared, which is then the square root of 28 over 2. Okay. And if you compare that to all the work we had to do to get to that point, I think you can see that's kind of a lot quicker, right? To kind of get to the simplification step. All right. The next thing here, just a couple examples of some different things here with this stuff is, rationalizing. All right. So rationalizing, when you have, radical in the denominator, but that you have a binomial. We talked about this before when we did complex numbers. Okay. That you have what's called the conjugate. Okay. So if you have, something along the lines of a square root of b plus c square root d. Right now, b, this could be 0. So it could just be a plus c times the square root of d. So these numbers here, different variations, that the conjugate of that, right? The conjugate is going to be a times the square root of b minus c times the square root of d. Right? So those are conjugates of each other. And we use that along with the, the fact of basically that a plus b times a minus b, this is our difference of squares, that this would be equal to a squared minus b squared. All right, so we use that, and then that helps us rationalize now when we have more than one radical in the denominator separated by addition or subtraction. So let's do an example of that. Do one, I guess, of each. So let's go with this one, 3 over 6 minus the square root of 2. So I want to simplify this by getting, right, it's not considered simplified. There's nothing mathematically wrong with this, okay? But the process of simplifying has to do with making an answer look one way, and really comes back to before calculators. It was easy to calculate and do work by hand when the radical is in the numerator. So in order to get this square root out of the denominator, we can't just multiply by the square root of 2, because we would get rid of this square root, but we'd put a square root over with the 6. So what we have to do is we simply multiply by the conjugate, 6 plus the square root of 2. All right. And when we do that, we distribute, we get 6 times 6, which is 36. We would then have 6 times the square root of 2 minus 6 times the square root of 2. Those cancel. And then you get negative times the positive is a minus, negative. And root 2 times the square root of 2, right, is 2. And now we've rationalized. We had a radical, an irrational number in the denominator. Now it's 34 rational. Up top, we can distribute, okay? Sometimes I might suggest not to distribute if this is going to simplify. So looking ahead, in other words, if I left it like this, 3, 6 plus the square root of 2 first. And then down here I have 34, but does 3 go into 34? No, so that's not going to simplify anymore. So then maybe I write an end result as 18 plus 3 root 2 over 34, like that. And then that would be done, okay? You might have something along these lines. Maybe you have a 2. Here's another one, divided by the square root of 3 plus the square root of 2. So now we want to get rid of these radicals. And so what do? We multiply by the conjugate. In this case, would be the square root of 3 minus the square root of 2. Now this negative, we could keep it up here. We could also, if we wanted, you pop it right out front. Okay. Sometimes it's a little easier to do it that way. That way you have a negative out front. There it is. And then we just worry about distributing the 2. So we have 2. Now, this is like I said, I'm going to leave this right now up here as like that. And now it's the bottom. We have square root of 3 times the square root of 3 is 3. And then I have, this would be root 3 times root 2 is minus square root of 6. And then plus the square root of 6. Those cancel. And then if positive times the negative is minus. And then square root of 2 times the square root of 2 is 2. And you see 3 minus 2 is 1. So then we get, well, no denominator. It's just 1. So we have negative 2, and we can distribute that. And you get negative 2 root 3, and then plus 2 square root of 2. All right, so if we do that, then that one is now finished. There you go. There's rationalizing denominators when you have square roots in a binomial. All right, next quick thing here is like radicals. Okay. Like radicals, okay, means same radicand, same index. Okay, same radicand, same index. Now, here we go. We got here nth root. Okay, A, this is my radicand, and then this is my index. So much like terms, right? You can add or subtract like terms. You can add or subtract like radicals. How do you know if they're like radicals? You have the same index, same radicand. Now that's in radical form. If we look at this, right, this is a 1 here. All right, if we look at this in exponential form, that would be then what? A to the 1 over n. So now, what's the radicand when we look at exponential form? This is a radicand, but that radicand is over here, the what? This is now the base, right? So we can think of this base, and then here, this is, well, my exponent, okay? Which now makes sense when you think of like radicals, that what are like terms? Same variable, same exponent, right? Same, well, variable, this would be like the variable is the base, and then the exponent up here. So that's our like radicals. And we have like radicals, you can add or subtract them like you would add or subtract like terms. Okay. So if we look at something like, let's go 7, a little example here, right? 7 times the 5th root, 12, right? Minus 3 times the 5th root of 12. Okay. Just think of these as things. I have 7 of these things minus 3 of these things, and these things are the same. So if you have 7 of these minus 3 of these, you would then have 4 of these, and these are the 5th root of 12. Done. That's it. I mean, subtract those because they are like radicals. Okay. You might see it in exponential form. For instance, you might have 4 times 9 to the 2/3 plus 7 times 9 to the 2/3. Now, keep in mind, don't do this. Don't make this 36 to the 2/3, right? That's a mistake I see. You make this 36 and 63 to the 2/3. No. Exponents first. You'd have to do 9 to the 2/3 first, okay? So in this case, though, I do have like radicals, okay? They're like terms, same base, same exponent, okay? If I converted this to radical form, this would be what? Cube root of 9 squared plus 7 times the cube root of 9 squared. In either case, they're like, you can see they're like terms. You have what? I have 11, in this case, times 9 to the 2/3. Or down here, I would have 11 cube roots of 9 squared. Okay. Now, here's sometimes this gets a little tricky because this really isn't simplified yet. We're talking about completely simplifying, because one of the things that when we simplify is we want to have any perfect, in this case, cube factors out of this, whether it's in either form, really. So it's probably easier to look in exponential form. I have 9 squared, but 9 is 3 times 3. So I really have what here? This is equivalent to 11 times the cube root of what? I have 3 times 3 times 3 times 3. I have 4 3's multiplied. Well, 3 of them are going to be 27, right? So there's 3 4's or 3 multiplied times itself 4 times. There's my perfect cube. The cube root of 27 is 3 times 11 is 33, and then what's left is the cube root of 3, right? So that really is now a couple of things. Combining my like radicals, whether it starts as exponential form, and then also simplifying. Okay. Now, another way you could do it here is write this. 11 times 9. 9 is 3 squared, so that's 3 squared to the 2/3. And then this would be equivalent to 11 times 3 to the 4/3. And now what I generally would say here, a way to do this one is when you have your base here, right? And this, anytime this is at least 1, it's going to simplify, right? 4/3 is more than 1. So this is going to simplify, right? And one way you could do this is just write it as a mixed fraction, 3 to the 1 and 1/3. Right? 4/3 is 1 and 1/3. Okay. Now let's think about this. When I had this property, a to the m, I wrote this down, I did this, a to the n is equal to a to the m plus n. When you multiply like bases, you add the exponents. And this is what I said. We don't work this way a lot of times, but here's where it's valid. You can understand that a to the m plus n, I could separate into a to the m times a to the n power. So 3 to the 1 and 1/3 is equivalent to now 11 times 3 to the first times 3 to the 1/3. And you can see here, I get my 33. And then I have left here 3 to the 1/3, which would be in radical form, the cube root of 3. Okay, so we can simplify our exponentials form that way. I think that's a good way to go. All right, let's do another one of simplifying here. Let's do the 5th root of 3/4. All right, so 5th root of 3/4. So how do you simplify this one? Well, it's not simplified because we have a fraction in the radicand. All right, so how do we take care of that? Well, in this case, we could just break it up and say, oh, that means I could take the 5th root of 3 over the 5th root of 4. And you look at this and go, well, now it's not simplified because I have a radical in the denominator. So what am I going to do about that? Well, I got to get rid of it. I would strongly suggest that if you look at your radicand, if this can factor, right, and you could simplify this and write it as a powers of primes. 2 squared, right? 4 is 2 squared. And then convert it into exponential form. So this is 2 to the 2/5. And up here we have the 5th root of 3. And now what do I multiply to get rid of it? Well, it's going to be 2 to the 3/5. And now 2 to the 2/5 times 2 to the 3/5 is 2 to the first. Done. I have 2. This is prime. And to the 3/5, which means that's not going to simplify because this is not at least 1. And now I have a 5th root. 5 in the denominator means a 5th root. I see the 5th root here. So then I have combined a 5th root of what? 3. And then I have 2 cubed underneath. 2 cubed is 8 times 3 is 24. So that is simplified now. Okay, that is simplified. Done. There's no negative exponents. There's no radicals in the denominator. The radicand is not a fraction. And this doesn't have any perfect 5th powers. All right, and you'd be done. That being said, this is another just no, don't do it. Don't do this. Don't take the 5th root of 24 divided by 2 and say this is equal to the 5th root of 12. All right. Don't just take 24 divided by 2. That's wrong. Don't do it. Okay. So there's a couple examples there. What I'm going to do, I'm going to stop this video. I'm going to make another one on the rest of the topic just to separate a little bit. Make sure as working through these, it's just a matter of these take some time. They can be difficult to find the best way to simplify. It's working, watching, thinking, making mistakes, see where you went wrong. There are times where sometimes students, you kind of go in circles and you just keep not simplifying. There's no quick way to really learn how to do this other than put a little bit of hard work and ask questions if you're confused, do some more problems, stuff like that. So watch over this. At points, without being in front of you, you could pause it, rewind it, listen again. All right, take notes. Listen to what I'm saying. If there's anything you want me to go over in more detail, let me know. We'll meet and we'll go over it. Okay.